writing me, make sure that everything went well. So I will talk about the rational geometry of BG. So this everything I will talk about is joint work with so, so let me first talk a bit about the motivation. So that XB is mode property variety over Q. Then the height of a rational point on your variety is defined as the maximum of the absolute values of the coordinates, where you may assume that we assume that the coordinates they are co-prime integers. So either in vector space, so we can multiply them by some rational number. But optimal case by rational number, we always assume these are co-prime integers, and then this definition of the height. More generally, if you have a very apolynomial L on an X, then you can define the height determined by L as the height given by embedding X into projective space given by the embedding defined by L. So the base question I'm interested in is if the rational points are infinite, then it is interesting to study, then you have many points, and then it is somehow interesting to study what is the distribution of these points. And how do you study the distribution? So we look at the number of points of bounded height. So for reasons you will have to always, you have to sometimes remove some set Z, which is a set of bad points. And after removing the set, you study the counting function n BLZ. So it depends on a real parameter B, on the laminar L, and on also the bad set Z. This is the number of points, rational points R Z, whose height is bounded by B. Okay. And so we nowadays have, I would say, quite a good conjectural understanding of this counting function, at least when X is Fano. So, and also assuming that there are rational points as well. The expectation is that there is a thin subset. So the function of thin, this will come back later in some other talks. I will not discuss it too much, but let's just say some geometrically controllable set and a positive constant A, and also a natural number N, and a positive constant C, such that the asymptotic number is C, your leading constant, times B to the A, times log B to the -1. And moreover, these constants A, B, and C, they're not arbitrary. We really have some kind of geometric interpretation of all of them. So in particular, the constant A and B, they depend on the place of L in the pseudo-effective cone. So let me make a clever picture. So let's say your Picard group is like the plane. And then the effective cone, is this area. And because X is Fano, the canonical divisor, it will lie somewhere here. And then at L, will it lie somewhere here. So what you do is you keep adding L to Kx until you hit here the boundary. It's Kx. That's AL. And then your A is defined as this number A, so this Kx plus L lies in the boundary. And B is the rank of the Picard group minus the codimension of the minimal phase of this cone, which contains this Kx plus L. And so I will also abbreviate this Kx plus L as which is called the adjoint divisor of L. Okay. And now let me talk about the leading constant. So there you really have to consider when considering the leading constant two cases. The first case is the L is known as adjoint rigid, or in other words, when the adjoint divisor is rigid. This means that there is a unique effective divisor D in the divisor class adjoint LML. In this case, expect that the leading constant is really a finite sum of Euler products. It's sometimes written in some slightly different way, but equivalently finite sum of Euler products. And the terms in this sum, they are indexed by the Brouw group. Okay, by the Brouw group of X minus D. So which is for the second cohomology group of X minus D. So somehow, yeah, we have, and also these other products also have some geometric description, but let me not talk about this, but so this means that this leading constant is really, it's very much related to a certain geometric invariance, the Brau group of your variety.
Is adjoint L kx plus L?
Yeah, the adjoint L is kx plus AL. Yeah, it's known as the adjoint divider, which is what it's called.
So the Brau group is
Yeah, it should be modulo.
constant or something
Yeah,
like
it
that.
should be modulo constant. Yeah,
Please.
yeah, definitely. Otherwise, too less. Yeah.
And is that finite? I mean, if
For
constant,
Fano, yes. Yeah, for the Fano variety.
but it's open. It's x minus d. It's not x.
Ah, yeah.
There could be some residues along the divisor.
Yeah, let me also conject that it's fine. Yeah, finite. Yeah. So if the other case, if it's not rigid, and in this case, you should consider the rational map defined by the adjoint divisor, which I call phi of L. So this is a rational map to some project space. Let Y be the closure of the image. Then you have some induced rational map from X to Y, and this is known as the Itaka fibration. And what you should then do is you should pick opens U in X and V in W That the morphism from U to V is well defined, not just a rational map, it's actual morphism. It's also proper, and you should also assume that the restriction of the adjoint divisors to each fiber is rigid. So this is possible to do. And you should maybe make it V even slightly more tiny in some cases. Then the expectation is that for a proper choice of Z, the leading constant is giving us a sum of leading constants of each of the fibers. So in each of the fibers, your divisor is rigid. So we have the description in terms of the sum of other products of Brau groups. But this VQ, this will often be very infinite, and so you get some infinite sum of leading constants for each fiber.
Okay, sometimes you need to remove the synset from V. Like, I think that
Yeah.
too.
Yeah, like I said, yeah, this is appropriate choice of
Right,
Z. Yeah, yeah. Sometimes Z might
Oh,
contain
I
a
see,
tiny
okay.
fiber. Yeah. Okay, so that's the motivation. The point is we want to sort of apply this, sort of generalize the conjecture to a more general setting. With a more general setting, this is for the stack BG. So what is a stack BG? Let G for now an already finite group, and K is a field with algebraic Galois of gamma K. Then we are interested in the inclusion of G extensions of K. Think of G extensions are being parameterized by some geometric object called the classifying stack BG. And to be very precise, the stack BG, it has rational points. So the rational points. So to be very precise, actually the stack, it is the rational point of a stack, they form a category, a group point. So the standard representation of this that you find in literature is as G torsors over the spectrum of K up to isomorphism. So the category with morphisms are isomorphisms. The second one, but is equivalently, which is maybe more arithmetic, is you can think of these as tau G algebras over K up to isomorphism. And what is often very convenient is you can identify these kind of things with morphisms, gamma K to G, up to conjugation. And so again, a category. So it might be that after conjugation, a morphism stays the same, but this means that you have an arrow in your category from the morphism to itself.
Sorry, if A is abelian, do you still need to include the categories of morphisms?
Yes, yeah, you always need to, yeah. Yeah, so if G is abelian, you basically get it. If objects are morphisms, and the only the objects are just morphisms from gamma K to G, and the morphism in your category, there are no non-trivial morphism between any morphism. They are only from one to the other, and they classify elements of. So that's the way we try to really think of this as rational points on some variety, and then try to study what happens. So yeah, so first question is, what does it mean to be in height on BG? So I defined the height in terms of mixed Briggs space, but of course it can't work because there are no interesting maps from BG to Briggs space. The only maps are the constant maps. So you have to do something for this. So essentially, in case of BG, without using the word stack, these heights were first defined by Ellenberg Venkatesh. So later, so quite recently, actually a couple of years ago, it was generalized how to give a height on any stack. And then but instead of them coming from vector bundles, instead of coming from line bundles, you have to consider vector bundles. So this is the framework of Ellenberg, Adriaan, and Zurich Brown. But then, like a year later, Darda and Yasuda, they found a different way of constructing heights on stacks, which is much more similar to constructing vector bundles, and which also is much closer to the case of Ellenberg Venkatesh for BG. So let me specialize this in the case of BG. What is the analog of a line bundle? I will assume that K is Q. Otherwise, you have to consider certain angular actions, which makes it a lot more difficult. But essentially, a line bundle is a class function, so a conjugacy invariant function, from the non-trivial elements of G to R, such that the image of G only depends on the subgroup generated by G. And we denote if we have a sub. We also, if you have a subgroup, when we note the value of any one generated also by F. So you can also think of these instead as morphisms from conjugacy classes of subgroups of G to the real numbers.
This kind of Picard group of B3.
Yeah, exactly. Yeah, it is sort of analog of the Picard group of BG. At least the real vector space. So yeah, so that's the next slide. We define pick or BG as a space of functions. An effective cone is defined as a subspace of non-negative functions. So why do we use the name pick or? This is related to, actually, I mean, it's essentially the name we word from Dada Yasuda, and the name seems to be inspired from orbifolds cohomology, where of orbifolds. You have some kind of similar things which show up there. So now, okay, that's what the line bundles are. What are the heights? So we start with a morphism from another graph to G. And then we define the height is what do we do? So we take the product over all ramified primes of your group. And then we take P to the power of F valued at the inertia subgroup of G. So you might say, okay, well, the inertia subgroup is not always cyclic, but it is cyclic for all with finely many primes. So the primes where it's not cyclic, so the primes we divide the order of G, you just put some nonsense, it doesn't matter. Really, only the tame inertia case matters. In the tame inertia case, the inertia subgroup is cyclic, so this definition makes sense. And yeah.
If you take FQT instead of Q, is it more complicated to define the analog of line bundle? If you have to.
Sorry, what?
If you replace K by FQT, is the definition the same, or take something more into account due to
so if QT it's the same, but for other extensions, if you look at the number field extension, then instead of having it only depend on the subgroup, you have a slightly different condition. And for example, over C, there's actually there's no condition on the subgroup. It's just an actual class function. But then over Q, you get class functions with only depend on the subgroup. And if you're in between, you have something in between. But yeah, this discriminant also makes sense just for FQT. Sure. So in this setup, let me talk a bit about some previous conjectures. So let me call the canonical class of BG the function, so the element of pick orb, which is -1 everywhere. Then again, we have pick orb. This is some kind of vector space. We have some cone of effective things in this, and we have some element kx. So we can define the A and the B invariants and the adjoint divider completely analogously to this case. And actually, if you then work out what everything means, it means the value of A is the inverse of the minimum value achieved by f. And b is then b is the number of values where it is achieved. So then there's the following conjecture. So the original version, which was without counting g extensions by discriminant, is due to Mallow. So let me then say what the conjecture is. It says if you have some positive function, then there exists a set of bad extensions and a positive constant such that with these choices of A and B, if you count the extensions which are not bad and such that the height is bounded by B, then asymptotic as B equals infinity, you get the exact same expressions as in the number field, as in the variety case. So like I said, original version of this is to Mallow. His case, he didn't include the set omega. It was realized a year later, essentially by Kluners, who found the counterexample of this version, who found that you really need to remove some version. Then Ellenberg Venkatesh again more or less wrote this down, although they again sort of didn't really mention the set omega. They thought about it some different way. And more recently, in this basically exactly the same version, the version in this precise sense is due to Tarja Suda. So the goal of the project me and Dan started is to understand what the leading constant is, inspired by the case of rational points. So we somehow in the rational point case we had an influence of the Brouw group and the attack vibration. So we want to find out what is the analog of this in this case. Okay, so let me also mention that the analog of the adjoint, so these are like somehow displayed by the rho, by you look at the set of elements in G, non-identity where your function takes the minimal value, but the adjoint is somehow the complement of this thing. But it turns out for this BG case, it's much more reasonable because under this subset is set. Remember this, maybe I'll write it down. Important. So first is about the Brouw group.
Is there like an analog in sense that if it's realized only one, it's the same as the rigid case?
Yeah, the rigid case is actually more general. But yeah, if for example, if the set is entire subset of G, then you're in the rigid case. But it's actually more general. The rigid case is more general. So yeah, so the definition of the Brouw group. So we can basically it just makes sense. BG, it has some good et al side, so we can make sense of the definition of the second et al homology of BG evaluated in GM. But unfortunately, in practice, if you start looking at these things, this group is way too large to give the correct answer. So then we have to do something different. And so the first idea is that if you have a smooth final variety and L is anticanonical line bundle, then the adjoint of L is trivial. So the Brouw group you have to consider just the full step, the full Brouw group. And the Brouw group is a stably birational invariant. So we can try to think of what is a stably birational thing to BG, and then take Brouw group of this thing. So what is this? You start with the faithful representation, and then AN mod G is essentially a vector bundle over BG. So if you instead take the stack quotient, then it is literally a vector bundle over BG. But you can instead take the variety theoretic quotient, and it is more or less the same as a vector bundle. Then you can take X as a projective smooth birational model of AN mod G, and then the Brouw group of X really should be the ramified Brouw group of BG. So important thing in this definition, of course, is that X is independent of the choice of representation. So this, yeah, it's a theorem. It's called a no-name lemma for some reason. And also, let me mention that the Brouw group of the study of this Brouw group, it goes back to Saltman, the question about Noether's problem, which is from the 80s. Okay, so, but we are, okay, this definition is nice, it works, but it somehow doesn't really lead us to note what is the definition of like this subgroup, this subgroup, the Brouw group X minus the adjoint. And so for this, we will take like different track. So if we have a variety, then we say that then Browell element, that the element of a Browell group of a function field is ramified if for all dvr R with fraction field kx, we have that B is in the Browell group of R. And if we put a ramified Browell group of kx is all the Browell elements which are ramified. So this turns out to be equal to the Browell group of a smooth proper model. So this is a nicer model. So the issue is for BG this doesn't work. Why? Because there's no really good reason of the function field. Okay, there is a function field, but it's K itself, which is not useful. So the solution is instead of only considering DVRs, fraction field is Kx, we just look at all DVRs. So if you have, more generally, if you have a DM stack X over a field, then we say that B is ramified if for all DVR over the field with fraction field K and a rational point, then we have that element, that the Browell element evaluated as rational point lies in the Browell group of the DVR. And we put the ramified Browell group of X is equal to the ramified Browell group. Yeah, all elements are ramified. So one question, of course, why is this equal to this if X is a variety? So in characteristic 0, this is very easy. I mean, it's not very easy. But anyway, you just take a smooth proper communication, and then you can show that they're both equal to the Browell group of this thing. Characteristic P pair is harder, but it is still true. So you can still show actually that these things are equal, which is and you can show that also this bloating is a stably birational invariant, and so it really agrees with this.
Do you use some purity results?
Yeah, we actually no for the we need some purity results for stacks more or less to show that's birational invariant. But once you have this, actually, to show actually that is equal to each other in characteristic P, this was inspired by an argument which shows so in the Colletilene Skobotov book, there's a theorem which says that you can check ramified by evaluation at like points in power series. So this is so here we over all DVR instead of power series, but sort of you can modify it.
But if X is smooth and proper, it's the same thing, or?
Yeah, it's like smooth proper. They're just the same as the actual Browell group. But sorry. But if a stack is smooth and proper, it's not. If you have a stack and it's smooth and proper, it's not the same. No, this is important. Yeah. This is so the ramified Browell group. The point is that not every K point leads to an R point. So being pullback of XK is not the same as applying in BRR. Yeah. Oh, this is important. Yeah. Because BG is smooth and proper. So this thing for BG is different than this thing than the usual Browell for BG. So this ramified Browell group, it seems to be correct when F is on the canonical line bundle. So as evidence for this, so it turns out a lot of cases in literature, that actually the Browell group is trivial. So maybe not so interesting. But there are some cases where the Browell group is trivial. The main case is the work of Mackie on Boolean extensions. And a second case is no published result of Koeman-Spejano about certain nilpotent extensions. And so we can show in both cases that relevant Browell groups agree. But like I said, general the Browell group should depend on F. So how we deal with this? The point is that if you sort of study this definition, you can sort of split your K points depending on the type of inertia they have. So a K point, that's me. A K point is like a map like this, right? But K the DVRs actually there's also some inertia subgroup. Okay, let's assume character 0, so there's a cyclic. And so this defines a cyclic subgroup of G. And so you can split this up into, again, this is defined, well defined up to conjugacy. Sorry. The cyclic subgroup turns out to be defined up to conjugacy. Yes. So depending on the cyclic subgroup you do, you really get a condition at each conjugacy class of G by splitting the K into the lambda. And then using only the conditions given by MF, so not looking at all extensions, okay, but only those for which inertial length in MF, we get a larger Brauer group, which we call the partial ramified Brauer group. And this seems to be the correct group when counting. And this is important because already for Z mod 4, the partial ramified Brauer group can be different than the usual Brauer group. So it's a very small group, right? So now about the generalization of the attack vibration.
So when you say this seems to be the one correct for counting, you mean that you have some kind of analytic set and you look at the part which is orthogonal to this unverified thing?
So you have some kind of analytic set and you can look at the things orthogonal to this subset. And this makes sense and it agrees with all the cases you're gonna find them. You're gonna find a measure on this analytic set. And I think it seems to be correct because not like there's some overwhelming. I mean, there's no other. We'll talk more later. There's some theorems in this field, but not like an overwhelming number. Right? This is definitely true. So, but you can have more pathological behavior than just some finite sum of Euler products. So there's a theorem due to Cohen, Diaz, and Olivier, which is if you count the number of D4 extensions and you count D4 extension. It contains two quartic subfields. You fix one. It is sort of given. Then you count by the discriminant of this quartic subfield. They do this, and they find actually that the leading constant is the infinite sum of Euler products, and the terms in your infinite sum are parameterized by quadratic extensions K of Q. And where is quadratic sum come from? But you look at is a map from D4 to C2. They compose this thing. So every D4 extension gives a quadratic extension. And each Euler product corresponds to only counting those extensions such that this composition equal to AK. So this seems to be some kind of Ithaka vibration. And in this case, okay, we see that the vibration is BD4 to BC2. Now, the vibration, I mean, whatever it is, it should somehow have the property that every fiber of it has the same A and B invariance as the original thing. Okay, up to a finite set of bad fibers. No, sorry, not a finite. Up to some set of bad fibers, whatever. And it should also be maximal with respect to this property. And basically, if you just take that assumption and then do some group theory, you find that the vibration is given by BG to B of, you take the group G and a quotient by the group generated by the minimal elements. So this, we say this is the attack vibration for a stack, for BG. So important thing in this thing is that not every fiber of this map is of the form BH, where H is a finite group. There can be two, this is, in the formal sense, this is a GERP. But there can be two cases. Either it contains no rational points. In this case, it doesn't matter for counting, so we ignore it. But it can also contain rational points. In this case, it turns out that it's always of the form BH, where H, instead of being a finite group, is a finite group scheme. And so for the type connection to make sense, we really have to work in generality of finite group schemes with finite groups. That's actually we do everything both generality. So now let me.
I have a question. So
Yeah.
you define some kind of Ithaka vibration here, right?
What?
You define some kind of Ithaka vibration.
Yeah.
Right. So is it coming from some kind of sector or something? Like I mean, like a Ithaka vibration.
Yeah.
In the case of variety, is coming from line boundary.
Yeah.
So my question is there something sort of line boundary here?
Yeah. So you basically look at. That's sort of the analog of the adjoint line bundle is a line bundle, which is also the function, which is 0 at mg and 0 nowhere else.
Oh, I see.
But sort of the entire, it's sort of no natural to look at mg instead of the complement. So based on this and some other things, it seems sort of that BG, it's a proper smooth stack, but it somehow doesn't behave as a proper variety in certain ways. It behaves somehow as it is an open subvariety of a proper variety, and such that the boundary components of this open subvariety are conjugated classes of things. So actually, so you have like BG, which is open, and then somehow you have like boundary components. Someone else just each component somehow corresponds to running it like if you look at the quotient. C is a conjugated class. And G acts by C by conjugation. So somehow this, this is in some sense what seems to be happening, and it's not so clear why this is true. And so why do you want to say it? For example, these boundary components, they generate analog of the Picard group, and they also generate analog of the fictive cone in some sense. And also, you know, why would you say it's not wave of the proper variety? So, for example, one formal reason why there's no wave of the proper variety is that the naive generalization of the volatility criterion of properness fails. So, that P elements of BG correspond to the ramified G extensions of QP, but not every ramified every extension of QP is ramified. So these are quite different categories. And so here's an open question. I don't know. Can this philosophy be made precise? Can you really find some kind of stack with generic has a BHA as an open thing and with components that then these things parameterized by now another question is, so we have given this definition of attack vibration, but actually there are two that they generalize this notion of the orthogonal K group and this pseudo-effective cone. For general the first stacks, okay, to make general the effective cone, you need some assumptions, of course. And similarly, the definition of the ramified and its partial ramified Brown groups, we can also extend it to these cases. On the other hand, our definition of attack vibration is sort of very specific to this case of BG. And if anyone has any idea how to make sense of this for the general stack, sure. And I want to say, I think. Thank you.